Alright, today's asynchronous section is on logarithms. We're going to talk about adding and subtracting logarithms, recognizing bases, and using the change of base formula. Alright, so what exactly is a logarithm? Alright, a logarithm function is the inverse or opposite of an exponential function. That means they undo each other. So take a look at this graph on the right. Here we have the function y equals 2 to the x, and the function y equals log base 2 of x. Notice that the point 0, 1 is on the exponential function and the point 1, 0 is on the log function. That is because when you have an inverse function, right, the x is in the y switch. So every point that you have on the exponential red function, its x and y coordinates would be switched on the logarithmic function. So notice here we have the point 1, 2, and on the log function we have the point 2, 1. Basically it's a reflection over the line y equals x, which is this dotted orange line. It means if I fold this paper, if you thought of this as a piece of paper and I could fold it over that dotted line, they would match right up on top of each other. And that's what you know about inverses. Alright, so another way to talk about a logarithm is it's the exponent to which a specified base is raised to obtain a given power. So suppose I had right now the function 2 raised to the x equals 10, and I asked you what x is. Up to this point in your mathematical careers, you would not know how to give me that answer. You've learned how to solve problems with multiply, divide, add, subtract, square roots, nth roots. So you know that multiply and divide undo each other. You know that add and subtract undo each other. You know that if I take a number, like an x, and raise it to a power, to undo that you take the nth root. Alright, now to solve this problem, right, to figure out what this x is, that's where logs come in. So it's another tool in your tool belt. Now you're going to be able to solve problems where the variable is in the exponent. Now you're going to be able to break it out of the exponent. That's what we use logs for. Alright, so suppose I wanted to answer that question. What is x? What do I have to raise x to here to get to 10? Well, I could start guessing, right? I could guess a 2. 2 to the second power is 4. Too low. I could guess 3. 2 cubed is 8. Still too low. But 2 to the fourth power is 16. So I know this answer is somehow in between 3 and 4. And in fact, it is 3.322. That is the answer to log base 2 of 10. So take a look at this graph. Alright, so here we have the exponential function y equals 2 to the x. Alright, and notice that x here is our input, our independent variable. So if I plugged in 3.322, the output would equal 10. But that's opposite, right? It's switched, as we saw before, because they're inverses of each other when we do the log function. So if I plug in log base 2 of 10 now, where 10 is the output here, but now it's our input into the log function, the answer I get out is 3.322. Right, so let's practice changing a log function to an exponential function and vice versa. This is kind of analogous to if I were to rewrite a multiplication problem as a division problem, or a division problem as a multiplication problem. Right? We can always do that. If I want to figure out, take a number and divide it by 2, right? That's the same as multiplying by 1/2. You know, those two things would be inverses. So here I can rewrite a log as an exponential. So let's practice with this example. Alright, so here's the exponential form. Some base raised to x equals some number a. Alright, so in our case we can see that the base in this log function is 2. Right, there's the base, and now we're going to change it to our exponential form. So now that's our base. That's our big number b there, so we just write 2. Alright, and now we can see next that the 6 is in the position where x is here in this equation. Alright, so in our case, that's the exponent in our exponential form. So it's like here, I take the base on the log and I raise it to whatever it equals to out here. So in this case, 2 to the 6th power equals x. And x is in the position where the a is on our exponential form here. Alright, so real simple. Once you learn to see the pattern, it's not too hard. You take the base and you raise it to whatever is over here on the other side of the equal sign, and then it equals what's inside the log there, where the x is in this case. Alright, and you can go back and forth the other way. So if I were to give you this exponential form, you should be able to also write it as a logarithmic form. Alright, so how would we do it here? Remember, the big number, the base, would be here, where that b is, the 2. And then the 6 is what it equals to on the other side, and then that x is there. So the very first property we're going to learn about logarithms is the product property. Alright, basically is what it says, that if I have an addition problem with logarithms, look over here on the right side of this equation, right, and I have them to be in the same base, right, I just multiply the values here, m and n. So log base b of m times n is equal to log base b of m plus log base b of n. That makes sense when we do an example, alright? Basically, all it's saying is to add logarithms with the same base, you just multiply the numbers. So take a look here. Look, we have logarithms with the same base. So if I want to simplify this or write this in a simplified form, I keep the base the same, so it's still going to be log base 4, and all I do is multiply these two numbers, 2 and 32. Alright, so 2 times 32 is 64. So I could simplify or write this expression here as a single log function. Log base 4 is 64. Now if we want to get the answer to that, remember this would be like, what does this equal? Sometimes they're easy. We don't need a calculator. We want to know what log base 4 of 64 equals. Well, that would mean that 4 raised to some power is equal to 64. Alright, so now what do I have to raise 4 to get it to be 64? And that might be a familiar number to you. In that case, it's 3, because 4 times 4 times 4 is 64. Alright, so we have the product property of logarithms. Now we're going to talk about the quotient property of logarithms, which is just stating the opposite. So it's saying to subtract two logarithms, like I have here with the same base, all you do is divide the numbers. Okay. Alright, so suppose we have log base 2 of 32 minus log base 2 of 4. So according to this rule, all I do is I keep the base the same, and I just divide these numbers. So it's log base 2 of 32 divided by 4, which is 8. Now remember, if we want to calculate this, right, this one's not too hard. This is another one that's pretty common. So this would mean that 2 raised to some power is equal to 8. And then kind of by inspection here, we can figure out that it's 3 because 2 to the 3rd power is 8. So in some of your checkpoints, when they ask you to simplify something like this, they might actually have you simplify and write that log base 2 of 8 is in fact equal to 3. And yes, you can see that 2 to the 3rd power is 8. Alright, so now let's express this one as a single logarithm and simplify. Go ahead and pause the video and try it on your own. If you try that, you might have been a little bit confused because you would have noticed that I don't have a base, or it doesn't look like I have a base. But right here where there should be a base, you can think of there as being an invisible 10 right there. We call this the common log, right? And it's the one that's on your calculators. So when you see that log function on your calculators, it is in base 10. Alright, so to simplify this, notice we have a product here. We're going to use the product rule because we have an addition problem. So we can write this as a single log, right, using that product rule, which should state that in order to simplify this, I should just multiply these numbers together. Alright, so we get log, and it really is base 10, right? When I don't have a number there, 100 times 1,000 is 100,000. And now you could simplify that a little further, because you really remember there's a log base 10 here, and we want to know what that equals. So we can rewrite it. 10 to some power is equal to 100,000. And now what do we have to raise 10 to get it to be 100,000? Well, we can just count the zeros. Right? So in this case, we can see that the answer is 5. Now later on in this lesson, I'm going to show you how to calculate the log of some number. It doesn't have to be even log base 10. It can be any base using a calculator when it's not a nice whole number like this. Because what if this said 10 to the x equals 55 or 52.32? Right, then I couldn't do it by inspection. So we're going to talk about how to do that coming up. Alright, so why don't you take a moment to pause the video and see if you can simplify this expression. Alright, so you should have noticed this subtraction sign right away, right? Should have registered as I need to use the quotient property, right? So remember, add and multiply go together, and subtract and divide go with each other. That's kind of how I remember it. So all we do is keep the base the same and divide the numbers. Alright, so 48 divided by 12 is 2, and now we want to know what log base 2 of 4 is. So log base 2 of 4 equals what? Well, then I can rewrite this as an exponential, right? So 2 to the x is equal to 4. And now we can see that x is 2 because 2 squared is 4. So remember, in your checkpoints, they might actually have it, you simplify and write the answer in this way. They would say that log base 2 of 4 is equal to 2. Right, so that would be how they would have you simplify this. Alright, so we can do it again. One more practice with doing the product rule. So we have an addition problem here. And we're going to rewrite this as a single log. So when you're solving equations later on in subsequent lessons, you're often going to have expressions involving logs that you're going to try to write as a single log. So that's why we learn this rule. And vice versa. Sometimes you want to take a single log and break it apart. Alright, so according to this rule, I have the same base here. Remember, they have to be the same base. If this was a 5 and this was a 3, you cannot apply this rule. Alright, you'd have to do something first in order to apply it. But in this case, I can apply the rule because we have the same base on our logs. So I multiply the numbers. And I get that 625 times 25 is 15,625. So it's log base 5 of this number. And so that would be saying, what do I have to raise 5 to, right, to get it to be this number, 15,625. So maybe this will be a good one to revisit later, how I could actually just use the change of base formula to get this answer, or using identity properties. Right, and that would involve recognizing that 625 is a power of 5, and so is 25. So maybe this will be a good one to revisit coming up in the next slide. Okay, so suppose I want to subtract these two logs. First I check to verify they're the same base. They are. Well, that means I can go ahead and divide the numbers. Keep the base the same. So we get that log base 3 of 486 divided by 18. That's 27. So now we want to know what that is. So remember now, 3 then raised to some power equals 27. Alright, so then we can see by inspection here that x is equal to 3 because 3 to the third power is equal to 27. Alright, so now let's talk about some of the inverse properties that I was talking to you about earlier. Alright, so one of them is this. If I have log base b of b raised to some power, that is just equal to x. Because basically log base b of b here cancels out. It's just equal to 1. Because that would be like saying b raised to what power is equal to b? How about 5 raised to what power is equal to 5? Well, it's always 1. 1 times x is just x. So you can think of those two things as canceling. So we just get that it's 2x plus 1. Why? Because here I just can cancel. Whenever you see the same base and the same two numbers really right next to each other, like here we have 3 and 3, you can just cancel that whole out and it's equal to that exponent. So this whole thing just simplifies to 2x plus 1. Likewise, if I have a base and I'm raising it to a log with that same base, those cancel out and equal 1. And so you just get the exponent here, what it is raised to, so it just equals x as well. So for example, if I have 12 raised to the log base 12 of x, all of this here cancels out. And we're just left with the exponent, which in this case is x plus 7. And so our answer is x plus 7. So let's go ahead and use that to solve this problem. Then we're going to go and revisit that previous problem that I told you about. So here we have x raised to the log base x of 4 to the x. Alright, so our first step here is to notice that I have a base here and I have the base on the log that are the same. They're both x. That's when they can cancel out. Okay? So all of this cancels out and you're just left with that exponent. So in this case we're just left with the 4x that equals 24. And now we can go ahead and use our inverse operations and solve for x and get that x is 6. So another way we could have simplified, let's go back and take a look here at the power log base 5 of 625, right? And I think over here we had it either plus or minus plus log base 5 of 25. Would have been to recognize, like I said, that 625 is actually a power of 5. So I could rewrite 625 as log base 5 of 5 to the 4th power. Because 5 times 5 times 5 times 5 is 625. Likewise over here I could write that log base 5 of 25, and 25 is the same as 5 squared. So in this case it was to our advantage to write these numbers as a power of 5 because the base on the log was 5. And now we can apply the rule, right? Now we can apply our rules of logarithms. So earlier we said when we have a log base 5 of 5 like that, that cancels out. So we're just left with that exponent 4. Same thing here. So we have that log base 5 of 5 here, that cancels out. That's 1. I'm just left with the 2. So this problem simplifies down to 4 plus 2, which is 6. Alright, and if you recall on the previous slide, that is the same answer that we got. So if you're watching this asynchronous session, make sure that afterwards, right, you go back and you answer the questions in the course announcements. Before we do that, let's practice one more thing. Let's talk about the change of base formula. Alright, so this is how that we can actually use our calculators to calculate the value of a log expression that isn't a nice whole number. You know, before we were doing what 3 raised to what power equals 27. Okay, well that's 3. But what if it said 3 raised to the x power equals 15? Okay, now that's a little harder, right? Because now it's not a nice whole number that I can just calculate. Luckily we do have a way we can do it. Now if you notice on your calculator, right, you don't have something that says log base 3 or log base 2 or log base 12. right? You just have a button that says log. Remember, that's called the common log, which means it's base 10. So if I want to calculate log base 3 of 27 on the calculator, right, there's the way that I have to do it, right, is what we call the change of base formula. And basically, I can convert any base, any log with any base, to any other log and base that I want. So that's what this says right here. And of course, the one that we're going to be doing all the time is changing it into base 10 because that's what we have on our calculator. Alright, so this says that I should take log of whatever this large number is out here, not the base. Right, so in this case it's log of 27 divided by log of 3. And really this is base 10 when we do it on our calculator. That's the base we're changing it into. But now I can plug that in on my calculator. And if you hit log 27 on your calculator, you get this value. And if you plug log 3 in on your calculator, you get this value. And then you would divide them. Right, and so when you divide them, you get that log base 3 of 27 is 3. Now we didn't need the change of base formula to calculate this one, right? Because 3 to the third power is 27. But like I said, if this was a 15, then you would have want to calculate log of 15 divided by log of 3, right, on your calculator. So I just kind of remember the bigger number is the one on top, and the base is on bottom. And so here's one that you can't do, right, by inspection, or changing it back into an exponential, right? You'd have to use the change of base formula. So according to the rule, I just take the log of 32 out here, divided by the log of 4. And now it's just a calculator problem. So you go ahead and you punch those on a calculator. You divide them. And in this case, we get that that is equal to 2.5. So remember what that means. That means if I took 4 and raised it to the 2.5 power, then I would get 32. Right, which makes sense because 4 squared, 4 to the second power is 16, and it needs to be more than that, but 4 to the third power is 64. Too high, right? So we know it's somewhere in between 2 and 3, so the answer 2.5 makes sense. Alright, so don't worry about doing these problems. The problems you need to be doing are found in the course announcements.